Okay, numbers 1 and 2. We're going to work through 1 together, and then I'm going to have you try number 2 after I show you how this is. So here's the kicker. We have the graph of the derivative. And so that is what we're going to use. And for part A, we're going to find where the original f is increasing or decreasing. Then for part B, we're going to find where the original f has a local max or min. And remember, local is the synonym for relative. And then part C says if we know that there's a point at 0, 0, sketch a possible graph for f. Okay, so this is helping us understand what we did for the first derivative test. So do you remember how we had that big chart? And the one row were the signs. And when the first derivative was positive, what did that tell us about the original? Increasing. And when the first derivative was negative, what did that tell us about the original? Decreasing. So we're using that, but in graph form. So if we look at this picture, the derivative is positive above the x-axis. So here are the 2 spots where it's positive. The derivative is negative below the x-axis. So this would be where the original is decreasing. So how they ask the question is they want to know what intervals this occurs on. So I'm going to put increasing first, and that's wherever the derivative was positive. And I'm going to go from -1 to 0 is one of those intervals. The derivative is positive, so that means the original is increasing. And then it's also increasing from 3, and it goes past it to 5, so 3 to 5. And then it's decreasing where the derivative was negative, and so that's from 0 to 3. Okay, how's that first line feel? Weird, but okay so far? Okay, B wants to know where there are relative maxes and mins. Okay, this also was from the first derivative test. We looked at our chart, and when it went from increasing to decreasing, it was a max. And when it went from decreasing to increasing, it was a min. And how we can think about that with our picture, when the derivative is 0, that indicates we could have extrema. So at these 2 points, there could be extrema. So if we look at this left one, it goes positive to negative. So increasing to decreasing, that would be a max. So there's a max, and it's at x equals 0. We don't know the y value because this is just the graph of the derivative. We don't know what it's doing in the original, but we know where it occurs. And then this point right here, the derivative goes from negative to positive. So then it goes, the original goes from decreasing to increasing. So that's a min. There's a min at x equals 3. Okay, now for part C, we're going to sketch a possible graph. So that word possible, it means that there's not just one right answer, and it's not going to be like point by point accurate. It's just going to give us an idea of kind of the flow of the graph. And so we know where it increases or decreases. We know where the max and the min are. So I know that there is a max at 0 and a min here. And then the other thing they're telling us is it has the point 0, 0. So I know that I have to get to this point. Do that. So from -1 to 0, I'm increasing to the max. And then I'm going to decrease until I get to 3 and then increase for the rest of the way. That's one right answer. The only right answer, no way. But it has to have the things we know for sure. The increasing and decreasing has to match, and we have to have mins and maxes where we said they would. And that would be a possible graph. And you could, maybe you went really low and you kind of leveled out. Lots of options there. But that is what we're doing when we learn the first derivative test. This is the idea behind it. Okay, try number 2. And then we'll compare answers here in a second. See what you can do with that. And just kind of, it's not very good at this, but like the left point is at -2, x equals -2, and the right far point is at x equals 5. You ready for me to say intervals? Are we at that point? Okay, for increasing, -1 to 3, 4 to 5. For decreasing, -2 to -1, and 3 to 4. A local max at x equals 3, and local mins or relative mins at x equals -1 and x equals 4. Yeah? It's kind of weird. Like, does your mind feel like it's working in a way it's never worked before? It's, no? Kind of normal? Oh, okay. Well, that bodes well for you. AP loves these types of questions. All right. Usually people find this really challenging to think through, so I'm glad. Okay, now we are going to incorporate concavity. So that's what these, like on the left-hand column, 11 and 12, they talk about increasing and decreasing, mins and maxes, but then we're also going to talk about concave up and down and points of inflection. Okay, so still a graph of the derivative. So the first couple are going to be the same. And we'll start by talking about increasing. So this is going to be where the derivative is positive, and it's starting at 0. So it'll go from 0 to 2, and 4 to 6, and it's also positive from 8 to 9. So the derivative is positive, those are all increasing. It's decreasing where the derivative is negative, so 2 to 4 and 6 to 8. So same idea on those ones. Okay, then for B, the extrema, okay, well right here at 2, it switches from positive to negative, so that's going to be a max. Are there any others that go positive to negative? This is a trick question. Well, that switch, negative to positive. Any other that go positive to negative? Yeah. Okay, so here's the deal with 6. It's going from positive to negative, so it's increasing to decreasing. The derivative does not exist here. Okay, now, think about what that could mean. Is there a way that we could have a max, but the derivative does not exist? A cusp or a corner. Here's the thing. It also could mean that there's a break in the graph. It could mean that the graph is discontinuous. So what we would say, and this is kind of how sometimes they have it as answer choices, possibly x equals 6. Now, if you have to put ones that you know for sure, we don't know that for sure. We just know that it changes direction, but we don't know that there's an actual max there. Okay, now for mins, this is going to be when it goes from negative to positive. So then that will be x equals 4 and x equals 8. Okay, now for the concavity. Concavity deals with the second derivative, and we have the first derivative. So do you remember that thing where I said that the first derivative test always tells you something about one thing backwards? And so here's what we know. If you think about this as the original, and you think about the second derivative as the first derivative, I know, crazy. When this is increasing, the slope is positive, which means the second derivative would be positive and concave up. So whenever the first derivative is increasing, the second derivative is concave up. So to answer this, concave up, and the intervals where it's increasing would be 3 to 6 and 6 to 8, and you could also combine that. You can combine it to 3 to 8. I kind of like it separated because that tells me something weird's going on at that break in 6, but either way would be acceptable. Yeah, 6 to 8. Or 6 to 9, sorry. 6 to 9. Okay, then concave down. This will be where the first derivative is decreasing, and that's from 0 to 3. Okay, now, does anybody want me to say that again? That concept, because I will gladly do that. Anybody want to repeat on that? Okay, then points of inflection, the derivative of point of inflection is where the concavity changes. So where did it change from concave up to concave down? And according to this picture, it's where it changed from decreasing to increasing or vice versa. Only once. Where is that once? X equals 3. And that would be our point of inflection. All right, now we're going to try a graph of this. And these these I feel like it's easier to do with a pencil because you got to incorporate all this stuff. I kind of sometimes give myself, like I know at 2 and 6, those are my maxes. These are my mins. So I give myself that. So I know I'm going to go max, min, max, min. But I got to make sure my concavity matches that too, though. So that's why I erase. So then for concavity, I'm going to check concave up from 3 to 6. That matches. Concave up from 6 to 9. Should fix that a little bit. That's better. Concave down from 0 to 3. Point of inflection at x equals 3. Yeah, that changes concavity. I should do something else here. So at that x equals 6, it changes direction, but it has to be like a corner or a cusp. So that would be the best thing to do there. All right, I'm going to have you try number 12 out. This gets kind of wiggly with all the concavity. So when we have the first derivative, when the first derivative is increasing, then the second derivative would be positive, so then that would be where it's concave up. Okay, so that's going to be where your concavity changes. And it's where, like on this graph, where increasing changes to decreasing or decreasing changes to increasing. It's got a weird wiggle in there where it doesn't have extrema, but the concavity is changing. Because technically, all these spots, the concavity changes. You ready to hear intervals? Okay, increasing 1 to 6 and 8 to 9. Decreasing 0 to 1, 6 to 8. A max at x equals 6. A min at x equals 1 and x equals 8. It's concave up from 0 to 2, 3 to 5, 7 to 9. And it's concave down 2 to 3, 5 to 7. And then points of inflection at 2, 3, 5, and 7. How are we feeling on that one? anybody's mind boggled yet? Right. Yep. Yeah. Okay, here's what we're going to do because I still want to have time to go over start the test. Can